Hi everyone, today we're going to complete exercises 10A and 10B, which is all about tangents, normals, and rates of change. There's nothing new that we're doing today, this is all stuff that you've already previously learnt. And before we go on, I just want to apologise for my voice as I'm a bit unwell at the moment, so it might be a bit croaky throughout the lesson. So today we are learning about tangent and normal lines and rates of change of various functions. What you need to be able to do is find the tangent and normal line of a function given gradient information, find the average and instantaneous rate of change of a function, and find the position, velocity, and acceleration of various models. Let's start with 10A, tangents and normals. So just to define these two, a tangent is a line that touches a curve at one point. So if I have a curve here, here's the one point, that there is the tangent point, and this is the tangent line. The really key thing about this is that the tangent line has the same gradient as the curve at that point. So that's the biggest thing. So if this has, y equals mx plus c, that gradient there is the same gradient at that point. And that's why tangents are so important to us with calculus. A normal line, or actually, we'll get to that in a sec. How do you find a tangent line? So there's 3 easy steps to do it. The first thing you want to do is find the derivative of a function. Substitute the x value into the derivative of the function to be able to find the gradient. So remembering again, the tangent line is just a straight line. It's just y equals mx plus c. So first thing you want to do is find that derivative, which will give me the gradient. Once we've done that, we need to find a point so that we can sub in. And the point, to be able to find that point, you need to find the y value, because usually they just give you the x. So you'll usually just substitute this x into the original function. So sub x into the original to give you y. And then once you've got your y and x, you can sub it in. You can use this equation. I tend to prefer this one just because I feel like it's easier, but you do whatever you like. All right, so let's start off with example 1. It says find the equation of the tangent to that curve at the point where x equals 1. So exactly as we said before, we know the equation of the tangent is going to look like y equals mx plus c. So the first step is to find that gradient, and the way we want to do that is to be able to find the derivative, sub in your x value, and then that tells you the gradient at that particular point. So in order to do that, I'm going to derive this function. So I'm going to get 3x squared minus 4x, and that's going to be my derivative. Now to find the gradient when x is equal to 1, I just have to sub in -1 into that function there. So dy by dx, so the gradient at that point is going to be 3 times -1 squared minus 4 times -1. Now when you work that out, that's going to be 3 plus 4, which is 7. So that tells me that when x is -1, the derivative is 7. Now that I know that, I want to sub it in. Before I can substitute it in, I need to find a point to sub in also. I know that x is equal to -1, I just need to find the corresponding y value. So to do that, when x is -1, I'm going to sub that into my original equation in order to be able to find that y value. When you work that out, you get -6. So the point that this tangent line is going to pass through is -1 and -6. And once you've got that, now I've got all of the points that I need in order to sub it into y equals mx plus c. So when y is -6, the gradient is going to be 7, the x and plus c. And then that's our only task. We just need to now find what is c. So it's going to be -6 equals -7 plus c. Take the 7 over, you get 1. Therefore, y is going to be equal to 7x plus 1. And that there is your tangent line. Now, how does that relate to normal lines? Well, normal line is just simply the perpendicular line to the tangent. So if I have a curve and here's my tangent, so it's got the same gradient, the normal line is the perpendicular line to it. So if this gradient is m, we call this gradient n. And the way you find that is it's just the negative reciprocal of your gradient. So in order to find the normal line, it's actually very much the same. There's just one extra step. So once you found the gradient, you just need to find the normal gradient. So that's just flipping it, chuck a negative in the front, and then you can sub it into the equation and everything is the same as tangent lines. So we've got this one here, and we're going to do a very similar thing to what we did before, that we want to find the normal. So our equation that we're looking for is y equals nx plus c. The first thing we want to do is find out what that n is. Well, actually, before we find n, we need to find m. Yeah. N. Then we need to find our x and y values to sub into the equation, and and then we sub everything into this to be able to find it. So step 1, we just need to derive the equation and sub in our x value. So let's go ahead and derive it. That's going to give me 4x minus 3. And then when x is equal to a half, the gradient is going to be 4 times a half minus 3, which is going to be -1. So that's my gradient when x is equal to a half. Now for the normal, I just need to flip it and chuck a negative in the front. So it's going to be -1 on -1, which is going to give me a normal gradient of 1. So then we have x, for the next part, we need to find the y value. So when x is a half, we're going to put it into our original equation in order to find y. It's going to be a bit yuck because of the fractions. So that will be a half squared is a quarter times 2 is a half. And that's going to be 3 on 2. And then if I change this to be the same denominator, 2 on 2, then I can go 1 minus 3 is -2, and then plus 2 is actually going to be 0. So that's quite nice. So the point that this normal line touches is a half and 0. So I've now got everything that I need to sub it into the equation. That's y equals nx plus c. When y is 0, n, the normal gradient will be 1. X is going to be a half, and then plus c. So it's 0 equals a half plus c. C equals negative a half. Therefore, my final equation is going to be y equals, what do we say n was? 1. We can just write that as x and minus a half. So that there is going to be my perpendicular line, what we call the normal line. All right, so just a couple of points about this. If two functions have a common tangent, then that's meant to say they will touch at one point. So what they mean by that is if I've got a curve here and then I've got another curve that has the same tangent, then the idea is that they touch the same tangent line. So the gradient at that point is the same and the point that it passes through is the same. Therefore, these two equations or functions are going to touch. All right, so the next one, to prove a tangent exists. I reckon that's meant to have an S at the end there. So how do we actually prove this situation that two functions have a common tangent? What you can do is, first of all, just show that the curves are going to intersect only once. Because if they only intersect once, then it's got this situation where they touch and then fly off to the other direction. There is also a chance that the curves can intersect more than once. And that's when, you have a tangent here, but then maybe the functions do this, where obviously this is not a tangent, but this is not, they don't have a common gradient there, so that's not it. But this point would lead to a common tangent. So what you can also do is, when you have those points of contact, if you're able to show that gradient is the same, then it'll prove that tangent, that they share a tangent. Whereas here, obviously, if you try to find the two gradients of the lines, they're not going to have the same gradient because they're going in different directions. So that's an intersection, whereas this is a point of like touching. It touches each other. It's got a tangent at that point. So that's just a little bit of an application to it. All right, that's the end of 10A. Let's now move on to 10B, which is all about rates of change. And again, this is all stuff that you've done in year 11 and previous years. There are two types of rates of change. The first one is the average rate of change. So this is the key word. As soon as you see average, we are not talking about the gradient. We are talking about the formula y2 minus y1 over x2 minus x1. So what you have to do when it's an average is you just have to find 2 points and then substitute it into that formula. So often we use it with curves. I don't want the exact gradient at any point. I just want to know what the average is. So if I were to draw a line between 2 points, what would the gradient of that line be? So find the 2 points, sub it in, and that will give you your average rate of change. Now that is different to the instantaneous rate of change, because instantaneous means what is the gradient at that exact point? And simply, as soon as you see the word instantaneous, or sometimes it doesn't say anything at all, but it implies it. So if it says rate of change, then it's asking you to derive the function and sub in x. And even though, this is just the first principles formula, which obviously we don't use, you just use your differentiation. So we're finding the derivative f dash of x or dy by dx, whatever the notation might be. So you just have to remember that average is your y2 minus y1. situation, and instantaneous, you find the derivative. So that's the difference between the two. All right, one application to this, which you would have started looking at last year, is something called kinematics, which is essentially just looking at the motion of a particle and moving in a straight line. We only look at it straight lines in methods. So there are three kind of equations to motion, or three parts to it. So the first one is position. So a particle will always have some sort of a position, and that position is relative to the origin. So if that's 0 and a particle has a 2, it means it's 2 away from the origin. It can also have a position of -2, which means it's 2 but to the left. Now the derivative of that actually gives me the velocity, which is sort of like speed, but it's not the same. Velocity also has a direction, so you can't have a negative speed, but you can have a negative velocity, which indicates that it's moving to the left side or downwards. So you can see that I've got my position is x, and the velocity, which we call v, is the derivative of that position. And then the derivative of that actually gives me the acceleration. So acceleration is the derivative of the velocity with respect to time. So you just need to know to move between position, velocity, acceleration, you just need to derive. And when we go to integration, you will need to antiderive to go backwards, which we'll talk about later on. So as long as you remember those three, we can then go ahead and apply it. So example 3 says for the function f of x equals log e 2x squared plus x, find the average rate of change. So keywords average there from 2 to 3, and then you need to find the instantaneous. So average tells me I've got my gradient formula, y2 minus y1. Instantaneous means I need to derive the function. So let's go ahead and do that. We'll start with part A. In order to find the average rate of change from 2 to 3, I need to find the 2 points. So when x is equal to 2, I could have just written it like that, log e, that'll be 2 times 2 squared plus 2. So 2 squared is 4, times 2 is 8, plus 2 is going to be 10. So my first point is 2 and log e 10. And then when x is equal to 3, is equal to log e 2, 3 cubed plus 3. So that'll be 9 times 2 is 18 plus 3 is going to be 21. So what we now know is that when x is 3, y is log e 21. Now it's just a matter of subbing it in. That's x1, y1, x2, y2. Alright, so y2 minus y1, that's going to be log e 21 minus log e 10 over 3 minus 2. 3 minus 2 is just 1 for the denominator, and then at the top, when you subtract 2 logs, it becomes 21 on 10. So that is your answer for that one. So that's the average rate of change. Now, to find the instantaneous is actually a lot more straightforward. All we have to do is derive the function and then chuck in 3. So first of all, we're going to find the derivative. Now remember, when we derive a log, it's the derivative of the inside over the inside function. So the derivative of that is 4x plus 1, and then that's just 2x squared plus x. And then we want to find the derivative when x is equal to 3. When you work that out, that's going to be 13 over 21. All right, next question. A particle moves along in a straight line such that its position relative to a point O at time t is given by that particular formula. So this is our position formula, x. Find at what times and in what position the particle will have a 0 velocity. So at what times indicates that we're looking for t. And then it also wants to know at what positions. So x equals, question mark, the particle will have a 0 velocity. So when is the velocity 0? Now what they've indicated, or what they've given us rather, is the position. I need to find what times and what positions that this function is going to have no velocity, or 0 velocity rather. So in order to be able to substitute v equals 0, I firstly need a v equation. So what I need to do is derive my function here to give me that. So we know that the velocity is equal to the position derived. So that's going to be 18t squared minus 9. Sub in 0 because we want a 0 velocity. I get 18t squared minus 9. What we're going to do is take the 9 over, divide both sides by 2. So we end up with a half. and then I'll take the square root, which is plus minus 1 on root 2. Now, obviously with time, you can't have negative time, so that means the time is going to have to be 1 on root 2 seconds. So that is when our velocity is going to be 0, and that's when the time. Then the next step, so now that we've found what time, we're going to find what position. So I need to sub in 1 on root 2 into my position formula to be able to find the relative positions. Cubed minus 9, 1 on root 2 plus 5. This is going to be a bit of a big job to do by hand. So when I cube a root, that's the same as saying that it's the root squared times another root, because it's cubed. And then we know that a root squared is just going to be the value inside. So that's 2 times root 2. So that's what I have at the moment. 2 root 2 minus, that's 9 on root 2 plus 5. And the 2 and the 6 can cancel. So that's 3 on root 2 minus 9 on root 2. And then I might as well just make this over the same denominator. So I'll end up with negative 6 plus 5 root 2 on 2. We don't like to end our answer with a root at the bottom. We want to rationalize it. So I'm going to multiply, or I'm going to, so in order to rationalize it, I'm going to multiply both the top and the bottom by the square root. So I'll end up with negative 6 root 2 plus root 2 times root 2 is just 2. So that'll be 5 times 2, which is 10. And then that can simplify with 3 and 5. So that is going to be negative 3 root 2. And because we like to write the negative on the inside, I'll write the 10 here. All right. So that will be the position when the velocity is 0. So a little bit messy, but that is how you would complete that question. Now for part B, it says, what's the acceleration at those instances? So the first thing I want to do is find what the acceleration is, which is by deriving the velocity equation. So that's just going to be 36t. So essentially I just want to find out what a is when t is equal to 1 on root 2. So I'll just sub in 36, 1 on root 2. What we can do is rationalize the denominator by multiplying both the top and the bottom by root 2. So that will be 36 root 2 on 2. And then when that simplifies, that's 18 root 2 meters per second squared. So with acceleration, it's per second squared.